Okay, in this lecture 19, we're going to talk about astrophysical black holes. Uh, the last lecture we talked about when you're getting closer to the Schwarzschild radius, uh, the, you need the full, because space-time is so curved, this parameter, Schwarzschild radius over the distance is, is comparable to order 1. So you need the full power of GR. And the Schwarzschild surface is what we call the event horizon, which is a one-way barrier. The particle of light can only go in but cannot come out. And also we talked about the fact a particle bound to a black hole has huge binding energy. Uh, and today we're going to talk about so-called astrophysical black hole, because so far we're concentrating on Schwarzschild black hole, which is an idealized static spherical symmetric entity. The question is this relevant to astrophysical phenomena? Whether there are these descriptions that can make any contact with physical reality. So we're going to first talk about some more realistic black holes that have spinning as angular momentum, and I'll talk about gravitational collapse of an ordinary star into a black hole. And from this, we're going to say something about the observation evidence for black hole. In the end, we're going to also start talking a related topic. It's called black hole thermodynamics. Uh, but anyway, mostly we're going to talk about astrophysical black hole today. So first, we're going to talk about the fact most stars rotate as have do not have spherical symmetry, but only axial symmetry. It's characterized, the star is characterized not by its mass, but also by its angular momentum, J. Uh, the solution to Einstein's equation for space-time exterior to such a rotating source was first discovered by Roy Kerr, the New Zealander mathematician and physicist, in the early 1960s, while he was in Texas. Kerr's solution has considerably more complicated singularity structure. Uh, it was, for example, instead of just like a Schwarzschild radius, a Schwarzschild black hole has a point r equals 0 singularity, and it was a spherical. Uh, this has a ring of singularity ring, and and as horizons, all these ellipsoidal rotation, and as compared with to the Schwarzschild black hole has a single point singularity and a spherical surface as an event horizon. So we'll talk a little more about the singularity structure. Okay. Uh, as said, in the Schwarzschild black hole, the event horizon uh, coincide with the surface infinite redshift. That's what we talk about. If I want a way to explain why it's an event horizon, it's surface infinite redshift. But in curved black hole, they're distinct. It was the infinite redshift surface is not equal to, it's not the same as event horizon, but it is coincide with something called stationary limit surface. Okay, so this ellipsoidal surface is station let me say, which is the same as infinite redshift surface. Uh, when a source rotates, GR predicts that the space-time would be dragged along. So here's a picture of a static source. Here represent the grid represent the space-time, which and when it rotates, it it drags the space-time along. So if a particle or photon starts with a vanished angular momentum L equals 0, one would normally expect it to fall straight towards the center of gravitational attraction. But with a rotating inertial frame reference, Since it's zero angular momentum particle will still develop angular momentum. It was a particle, whatever it is, it will follow the geodesic. But now the space-time is twisted, so that the geodesic is would tell the particle to follow an orbit that has angular momentum. What's called stationary limit surface is a boundary of region where the frame dragging is so strong, in which when you're getting closer to the black hole, the frame dragging is stronger and stronger, so that no particle, not even light, can be stationary. Meaning that normally you can stationary, you say, okay, it will drag along, but if I start with going the opposite direction, I can counter part of that. But the station limit surface, beyond that surface, everything rotates the same direction as the source, even if they enter with a great angular momentum opposite to the source. It was beyond that surface, nothing can, no matter how initial condition you have to rotate in any opposite direction or stand still. And so this different from the event horizon. So this region in between, which is marked as a gray area, is called ergosphere, which has a property that particle traveling in this region is possible to have a negative energy. And from that fact, we can actually show it's possible to extract energy from the black hole, from a rotating black hole. This is called the Penrose process. Now I'll come back to the binary energy question, but now I'll talk about spinning black hole. Let's remember, we're talking about particle in the smallest orbit around the Schwarzschild black hole, which is a static, non-rotating black hole, has the angular momentum this value and the size, radius of the orbit this value, and then you plug in find the energy of the particle, kappa. You find this equal to square root of a over 9. The point. So it's 94% energy of the rest energy, which means 6% is in the binary energy, which can release when particle bound into the orbit. Okay, this is huge compared with even in thermonuclear fusion, that's less than 1%. So this is 6%. So almost a factor 10 larger. But now for a spinning black hole, curved black hole, especially what's called extreme spinning. That's the maximum spinning value you can have given by the GR. Has this angular momentum, has this radius, and so it corresponds to the energy of the bound particle. It's exactly the same calculation, turned out to be only less than 60% of the rest energy, which means 42% of binary energy that can be released. Okay. So it's an extremely efficient mechanism to generate energy when it's bound into a spinning black hole. So we talk about all these static or spinning black hole, but there seems to be, we're talking about entities that always existed, have these properties. The question is that if we have a universe full of ordinary stars, uh, where does this black hole come about? So far, we said we talk about eternal black hole that always existed with mass behind its event horizon. So the question is whether GR will allow the creation through the gravitational collapse of more normal matter of a region of space-time with its features. Okay, so here we need to solve the Einstein equation with sources to see how they behave. Of course, the expected gravitational collapse. Then the question whether they will create that kind of event horizon and have that kind of singularity behind the event horizon. The most influential work in this area was by Oppenheimer and one of his young collaborators, Schneider. Oppenheimer, whole entourage of young collaborators, and they, as people said, they all talk the same way as Oppenheimer. But anyway, Oppenheimer Schneider wrote a paper in 1939. They did this analytic calculation of a radial collapse of course, some idealized matter, pressure-free fermions from a smooth initial distribution. and they showed the forms of black hole was probably discussed about horizon singularities. So still, there were a lot of reservations. People say, well, uh, its spherical symmetry is too idealistic because there are lumps, the shock waves, electromagnetic radiations, all these things. Whether they will lead to such spherical idealized situation, but is an approximate to reality at all. That's, of course, Oppenheimer did the work just before the Second World War. Then, of course, the war and the atomic bomb project, and the revival of the black hole study in the 1950s, particularly really through, because you mentioned computer and numerical calculations, to large part to the leadership of John Wheeler in the U.S. and Sadovich uh, in the Soviet Union. It's interesting to know that both Wheeler and Sadovich was also play a big role in the building of the hydrogen bomb in both countries. Anyway, Wheeler was also one who gave the black hole name. You probably heard about it. So, so therefore, basically, the numerical calculations show that even though with all these possible complications, you still obtain a black hole. Okay, but again, numerical calculations may not convince everyone. That's not only until the early 60s when Roger Penrose proved a whole series called singularity theorems, leading to final acceptance of the physics of GL prediction that black holes are the generic end product of gravitational collapse. Okay, so it was whatever complication you have, for example, show you have lumps, all these things, they all actually uh, smoothed out by gravitational radiations. And these theorems show that the real situation, the inevitability of formation of event horizon, with which always lies a singularity. Okay, so that's what we call singularity theorems. Related to these theorems, there's another theorem saying that all black holes can be completely characterized by the mass and angular momentum and electric charge if you have to have charge, but uh, that seems realistically that interesting case. But anyway, it's a very simple description. It's almost like elementary particle. Just so that came to Whitty saying that black holes have no hair because there's no complicated features. It's just like an elementary particle mass and angular momentum. So now we're talking about okay, so it is possible black hole can form through gravitational collapse of ordinary matters, but still, so we'd like to see uh, what's the observation evidence for black hole in our universe. Now, black holes are far away, small, black disk in the sky. Seems like hopeless to ever observe it. Turns out, what you can do is by looking for the gravitational effects of a black hole. Okay, on surroundings such as the gravitational lensing, the effect on the orbits of nearby stars, and the accretion disk of hot gas. We can estimate the mass of the object causing all these effects. If a highly compact source has a mass greater than, say, 3 solar mass, it is a strong candidate for a black hole, since no known mechanism can stop such a massive system from gravitational collapse into a black hole. Okay. So where does 3 solar mass criterion come from? Now, in ordinary stars, the gravitational attraction is balanced by outward pressure from thermonuclear burning in its interior. That's how many stars, our sun is balanced this way. When the fuel is spent, it's countered by quantum mechanical repulsion to the Pauli exclusions. Because Pauli, two particles cannot be in the same state. So therefore, there's effective repulsion, and this is called degeneracy pressure among fermionic particles, electrons, which is the degenerate pressure for for the white dwarfs, and the degenerate pressure of neutrons are the force holding up neutron stars. And here the big name is Chandrasekhar. Okay, in, because using the 19, remember quantum mechanics come about in 1925-26. Just so a few years later, Chandrasekhar, in fact, believes on his way from India uh, to England, came up with a new quantum mechanics calculation to show that for white dwarf mass greater than 1.4 solar mass, and that's of course Chandrasekhar limit, the electron degeneracy pressure is not strong enough to hold the gravitational contraction. So it was a quantum mechanics calculation to show that in such a situation, if the mass is greater than this, the degeneracy pressure is cannot hold up. It's not strong enough to hold up the gravitational collapse. So he was the first one to make the radical suggestion that such a massive star will gravitational collapse into nothingness. Of course, those days the word black hole has not been invented. But he was strongly opposed by the established physicists, notably notably the Eddington. Then, of course, in 1932, Chadwick discovered neutrons, and 1934, Sawicki, we can hear his name again, suggests that the remnant of supernova explosion associated with the final stage of gravitational collapse was a neutron star. Okay. Now, because of the strong nuclear force involved in such an object, there exists no simple analytic calculation for the corresponding mass limit, like in the Chandrasekhar for the electron case. But numerical estimates of neutron degeneracy pressure all points to a value not too much more than 3 solar mass. That's why the solar mass, 3 solar mass criteria come about. So now we're going to talk supermassive black holes. Okay. It's long been discovered that in the center of most galaxies there are supermassive black holes with mass in the range of a million to a trillion solar mass. And again, of course, this black hole discovered through the gravitational effects on its surroundings, like the orbits on nearby stars and the accretion of hot gas. The accretion of hot gas came about because magnetohydrodynamic calculation shows the black hole transformed into a luminous object when they acquire orbiting disk of it was this gas surrounding the black hole were basically lit up, so making the black hole. It's not the black hole itself become red hot bright object, but it's the surroundings, the accretion disk become bright hot objects. We can see them. Here's an artist's picture of the accretion disk. So a particle spiraling inwards through the disk will reach its inner radius, still outside the event horizon, having released its binding energy, as we said, from 6 to 40% of the rest energy before plunging inward towards across the event horizon. This can explain the enormous energy output at the center of some of the galaxies. And this is called active galactic nuclei, AGN. The famous quasi-stellar objects, has shown to have enormous energy output, are interpreted as AGNs in the early stage of galactic evolution. And the magnetic field lines coupled with the electric current flowing in the accretion disk can also give rise to relative outflow of jets. Okay, this again has been shows a lot of astrophysical phenomena. So here the takeaway of the first part of lecture 819. We said curved black holes are generic end product of gravitational collapse for stars over 3 solar mass. And black hole can be observed through their gravitational effects on surroundings, such as gravitational lensing and the orbit of nearby stars, or the accretion of hot gas. Because gravitational binding energy to a spinning black hole can be extremely large, it is a source of large energy output supermassive black holes. So that's and before we end lecture 19, we can start talking another topic called black hole thermodynamics.